Okay, so defining this without proving it, but we'll prove it soon. You can take this as a formula right now. Later on you'll be asked to prove it, and you'll be responsible for proving it. But the proof is very, very simple at the level of Algebra 1. Conceptually, one of the easier things in physics. Once you get used to it, it's very easy. Okay, so it's not difficult. So take my word for it, there's a reason for this, and you're going to understand it. And we're trying to understand it in terms of this example. So,
is that a M or an omega?
it's an M.
Okay.
I see how you could be confused. Okay. So again, just using the idea right now that there's a certain amount of what we call energy as a result of bringing these magnets into proximity, it gets converted to energy of motion.
Yeah.
Okay? And then, in the case of the car across the tabletop, gets dissipated against friction. Okay? So where does energy start?
It's not created or destroyed.
In order to get these things together, what did I have to do?
You had to force them together.
I had to push them together. Did you see me get out of breath when I did that? Well, I have good control. Where did the energy to push these things together come from?
Potential energy in your body that you push
Okay, yeah, but you know, we want to go to a more fundamental level. There's potential chemical energy in my body. Where'd that potential chemical energy come from?
That burger yesterday.
Came from breakfast. And what does every red-blooded American boy eat for breakfast?
Bacon and eggs.
Huh?
Wheaties?
Cocoa Puffs?
Wheaties?
Fruit Loops? No, Cheerios.
Like bacon.
So the energy comes from Cheerios. Cheerio is the basic unit of energy in the universe. Where do Cheerios come from?
We might actually like
Wheat and grain.
Photosynthesis.
Oh.
What do you need for photosynthesis?
the sun.
Yeah, and what comes from the sun?
Radiation.
Huh?
Radiation.
Okay, energy, right? And what's the basic unit of energy? The Cheerio. So you got Cheerios streaming out from the sun, warming things as they go. Okay? So the sun produces Cheerios, which then go through photosynthesis, produce Cheerios, which I eat in the morning so I have the energy to push these magnets together. That's conservation of energy right there. So you're enlightened. Yeah, we'll modify it a little bit maybe. Okay, so the whole point of this is that there's a source of the energy that propelled that truck across the tabletop. Doesn't come from superstition. Okay? There's connections. And we know very well what those connections are. And if you happen to think they don't really come from Cheerios, you can go on with your pathetic illusion and probably convince other people, okay? Now, kinetic energy is 1/2 mv squared, okay? And what we want to get a handle on is first the kinetic energy of that truck, right? Well, the truck has one mass, right? Okay, whatever its mass is, now I can tell you, you know, in SI units, it's about 43 grams. Actually, with a magnet on it, probably closer to 50. Okay? And the magnets that we're using have about 50 gram mass. Okay? Whatever that means, and we'll see so shortly. It's very simple. Okay? So, the truck gets energy to accelerate it to, let's say, 20 centimeters per second. We'll say 25, so we don't keep using 20. There's certain magnet proximity. Right? Now, here's our rotating axis. It's got a truck here, it's got a truck here. It's got 4 magnets here, and it's got a magnet here, and a magnet here, and it's got 4 magnets out here. Okay? I'm going to say the mass of the truck is M.
Have you checked that email? Are you waiting on it?
This mass is 4M. This mass is M. And this mass is M. This mass is 4M. And this mass is M. Okay? And the distances are, just to keep it simple, 10 centimeters, 10 centimeters, 45 centimeters, and arbitrarily 35 centimeters, okay? My question is now, now I'm asking what's the total kinetic energy of this system, this rotating system, okay? Now there's actually a meter stick and that metal beam on there that also carry significant amounts of energy, okay? And I'm not counting them. So we're just pretending this is all we have because we want to keep it simple, okay? So this is going to be a homework problem. If your angular velocity is omega, then what's the total kinetic energy of this system? Okay?
So we're supposed to get that in terms of omega?
Yeah, in terms of omega and the numbers that I have here, the masses and the velocities and this thing with kinetic energy, right? And then now you're going to want to use V for velocities of these, although you really should use like V1, V2, V3, V4 and stuff. Okay? You're probably going to use V, and I don't want to confuse the issue by using different V's. Okay? So I'm going to use a special symbol. That's a tilde over the top. There's one of those in the keyboard. It's V tilde squared. Okay? And that's going to actually stand for the velocity of the truck as it goes across the table. Okay? That makes sense? V tilde is some specific velocity. We haven't specified what it is. I want to know how the angular velocity omega of this system, or what would be the angular velocity of this system if you had this kinetic energy. Okay? And I'm going to actually break this into 2 parts. Okay? Because y'all are looking a little dubious. So instead of saying this, I'm going to use a capital K sub 0 for whatever kinetic energy that cart gets across the table, which you can easily calculate, okay? And then I'll use V tilde, and here's a little explanation of why I'm using a V tilde, but you don't really need that to do the mathematics.